Imagine you're sitting in a car outside a parking garage. As you slowly drive forward, the barrier gate lifts, letting you pass. Later, you're waiting at a railway crossing. As the train disappears into the distance, the barrier rises once again. Have you ever wondered how those gates know exactly where to stop? They don't spin around endlessly like a fan. They move to one precise position and stay there. Today, you're going to build the special motor that makes that possible. Last time, we turned a knob and watched an LED become brighter and dimmer. That knob was a potentiometer, and the Arduino used PWM to control the LED's brightness. Today, we're using that very same knob to control movement instead of light. That's one of the coolest things about engineering. The same Arduino can control completely different devices just by changing what it's connected to. PWM isn't just for LEDs. Think of it as a special language that Arduino uses to send carefully timed signals. An LED understands those signals as brightness, while a servo motor understands them as position. Same signal, completely different meaning. Now here's a question for you. What would happen if a motor never knew when to stop spinning? Picture a table fan. Once it's switched on, it keeps spinning for as long as power is supplied. Now picture your elbow. Your elbow doesn't spin in circles. It bends to a position and stays there. That's exactly the difference between a regular DC motor and a servo motor. A servo motor doesn't ask, "How fast should I spin?" Instead, it asks, "Where do you want me to point?" You simply give it an angle between 0 and 180 degrees, and it moves there smoothly before holding that position. If I asked the servo to move to 90 degrees, where do you think it would stop? Exactly halfway. And if I asked for 180 degrees? It would move all the way to its maximum position and stay there. So why can't we use a normal motor for a barrier gate? Because a regular motor has no idea where it's pointing. It only knows how to rotate. A servo motor is different because it has a tiny controller built inside that constantly checks its own position and makes small adjustments until it reaches exactly the angle you asked for. Just remember one simple idea. You choose the position. The servo finds it. Controlling a servo with Arduino takes only 4 simple steps. First, we include the servo library. Think of it as an expert helper that already knows how to communicate with servo motors. Next, we create a servo object, so the Arduino knows which motor we're controlling. Then we attach the servo to one of Arduino's digital pins. Finally, we tell it which angle to move to using a single command. That's all it takes. Now let's connect this with what you learned in session 1. Do you remember the map function? Earlier, it converted the potentiometer's reading into LED brightness. Today, it converts those same readings into servo angles between 0 and 180 degrees. Same input, same function, different output. Now let's build our automatic barrier gate. Picture the barrier arm blocking the road. As you slowly turn the potentiometer, Arduino continuously reads its value, converts it into an angle, and the servo smoothly lifts the gate. Turn the knob back, and the barrier gently closes again. In a real parking system, a sensor would detect the arriving car automatically, and Arduino would open and close the gate without anyone touching a knob. The wiring is simple. One wire supplies power, one connects to ground, and one carries the control signal that tells the servo exactly where to move. This simple idea is used everywhere. Railway crossings lift their safety barriers using position-controlled motors. Parking garages open their gates automatically. Robot arms use several servo motors, so each joint moves precisely. Camera gimbals keep videos steady. Even remote-controlled airplanes use tiny servos to control their wings during flight. Every one of these systems relies on the same idea: move to a precise position, hold it, and move again whenever needed. Today, you've discovered that not all motors are designed to spin forever. Some are designed for precision. That single idea, controlling position instead of speed, is what allows machines to automate tasks with incredible accuracy. So now your Arduino has learned two important skills. It can control light using PWM, and it can control movement using a servo motor. But there's still one thing it can't do. It can't sense the world around it. In the next lesson, you'll give your Arduino its very first sense: distance. Using an ultrasonic sensor, your project will detect approaching objects automatically and make its own decisions. Your barrier gate won't wait for you to turn the knob anymore. It will know exactly when someone is coming and open all by itself.